Welcome to a structural analysis video from the Ultralight Airplane Workshop. In this video, we're going to talk about aluminum sheet buckling. And in particular, I'm going to have an emphasis on wing skin aluminum sheet compression buckling. Now, I'm currently in the process of designing the UWS-4 ultralight airplane. It's a mostly aluminum airplane. I'm going to be using, or at least intend to use, aluminum sheet for the wings of the airplane. At the moment, I am designing the nose rib and roughly at the same time the main rib of the airplane. So right where those ribs meet with the spar, there's going to be aluminum sheet over that. And let me use my pointer here. On this main rib, right back in here, when there's compression here, there'll be compression when we have lift on the nose and on the main rib. This sheet up here is going to be in compression and it's going to want to buckle up. Now this main rib is going to be taking some of that compression down here where it's pushing against the shear rib and the nose rib. But the sheet here is going to take quite a bit of that compression too, a lot of it. So what I want to figure out is how much compression can I have? Now it's really going to depend on the spacing of these rivets, because I'm going to be using the thinnest sheet I can, which is 16 thousandths aluminum, although you can get 12 thousandths, but that's so thin it's really difficult to use. So what I want to figure out is what loading can I put on this sheet in compression with various spacings of this rivet. The farther apart I can put these rivets, the fewer rivets I'll have to have, and the lighter the airplane will be, and the less work I'll have to put into the construction of the airplane. Let's get to it. Before we get too far, I want to mention that we have two new designer tier patrons on the Ultralight Airplane Workshop. These are the names that they use in the Discord server of the Ultralight Airplane Workshop, and they're really active, so if you get on the Discord server, feel free to say hi. Now the compression loading we're going to talk about can actually be applied to a lot of parts of the airplane. Now here I'm really more concentrating on the skin of the wing, but it really applies to anywhere else that you have not a great deal of curvature to the skin. So like here on the bottom near the spar and at the top very close to the spar, what we're going to talk about on the compression loads will be fairly applicable. Now up here on the very nose where we got a really sharp curve, it wouldn't apply. And even up here fairly close to the nose, it probably wouldn't apply. But from roughly here on back and most of the bottom, it would apply. And while we're over here talking about this stuff, this is the airfoil for the wing. This is the nose. Here's the trailing edge. This is where the bottom spar would be. This is the web. Here's the top spar. And I've also drawn, for just illustrative purposes, kind of what the loads would look like on the wing. So you're generally going to have pressure pushing in to the bottom of the wing, at least at a fairly high angle attack, and then suction on the top of the wing. So you're going to have far more suction up here at the nose, and then it's going to start trailing off in roughly a triangular shape coming back here to the trailing edge. Now this over here is a top view of the wing. So all this light gray area would be the skin. This kind of medium gray area is where a rib would be. So there's a rib here, here, and here. This is the spar cap. These little white circles are rivets. Now I do not yet know what the rivet spacing is going to be. They're just kind of placeholders here. And then this blue dotted line here is where the force from the wing skin is transferred to the rib. So halfway in between the ribs is where you start considering where the force is. So within this area, all that skin force is being transferred to this rib and to the spar too a little bit. So here's a better cross-section view of what I'm talking about. So here's a view at the end of the spar cap, this blue area, kind of an angle aluminum. This would be the shear web for the spar. This black line up here is the top skin. This up here is the nose rib. This back here is the main rib. This dotted line that I'm showing here is the way it's going to bend in compression. It's going to bow out. Again, here it's going to bow out. Again, these are the rivets. Now when we have lift on this wing, we're going to have lift from the nose rib going up and lift from the main rib going up. This is going to cause this area in here to be in compression. Then there's also going to be shear that's going to be handled by this shear web. Each rib is going to be putting shear into the rivets here in the shear web. Now right now I'm drawing this with the 1¼ inch spacing from this rivet to this rivet. That is roughly the minimum spacing I would want to put in here. I don't really want to put them closer together, mainly because this rib's going to get too close to this area and want to tear out. And same thing for this rivet. It'd be getting a little too close to this area and then wanting to tear out. And then I'm also want to consider up to a 3-inch spacing. Let's find out how much compression we can handle in that situation. So let's look at the equation for calculating the skin compression, at least for a flat panel. Over here we have two different orientations for applying the force. These black lines are the force, so we have a long piece of skin, some flat panel, and it's fairly narrow here. And then we're representing the thickness here. So in this case, this height is less than the length. So this is the height here. Then we have this other orientation where we are spreading the force over a very long distance. So basically 90 degrees what we had here. These orientations will change this value up here. Over here, this is the compression value. This is the elastic modulus of aluminum at 10,000 pounds per square inch. Then we got the thickness here and the height. And then that quantity there is squared. And by the way, I got this from the book Flying on Your Own Wings by Chris Hines on page 178. And he also has some other stuff right there around that area that we're going to be talking about also. Now this constant K sub C also changes depending on these edges being fixed or free. So let's talk about that. Now I'm going to concentrate on where we have the force distributed over a fairly long length, where the length is much greater than this height here. So let's go back and look at the top view of the wing again. So that's what we're looking at here. So the force, the compression force, is here on the long side. And there's basically no compression force here on the narrow side. So that's why I drew this box here. And I mentioned how this edge over here that doesn't have the force, how it's fixed or free will change that K sub C. So we have this drawing here, this graph, where K sub C is over here on this vertical bar. And then the ratio of the height over length, which is this height and length, is down here on the bottom. So we have this graph and this graph. So this top graph is related to this. So here where I have these lines, that means all the way around this piece, which is this piece over here, this is fixed. So it's not really free to move. Whereas down here, we have the forces coming in on this side. This is fixed, and it's fixed with the rivets. But this edge here is completely free. So for an example, over here on this rib, if we had this box over here, this is actually where the outer panel of the wing attaches to inner panel. So this is going to be free. Whereas in here along this line, this is going to be fixed. Now, it's not rigidly fixed because this is slightly flexible in here. There's nothing to support it except the skin itself. So in reality, up here where we're showing this edge to be fixed, it won't be truly fixed. So the load we're going to calculate for this condition will actually be a little bit less. Now, what I'm going to do is I'm going to do the calculation for this condition and this condition, knowing that for this wing, we're actually going to be somewhere in between in here because we're not rigidly fixed and we're not completely free for most of the wing. So I can at least calculate what the bounds are going to be. So let's go ahead and start doing some calculations. Now I'm not going to go through step by step on these calculations. I mean, you can see the equation, you can plug in values just as easily as I can. But let's talk about some of the dimensions I'm going to use. So first, let's do a calculation where the height is 1.25 inches. Now, what about the length? So I said this height here, 1.25. What am I going to use for this length? In other words, how long is this box going to be? I said it wasn't going to go edge to edge just because of how flexible would be clear out here. So we're going to come in a little bit. That's actually going to give us a conservative estimate, which is good. So I somewhat arbitrarily decided to use 6 inches along the spar. That's because I think I'm probably going to use 3-inch spacing for the skin on the spar. So there would be a rivet here, a rivet here, and a rivet here. So it's 3 inches to this rivet, 3 inches to this rivet. So right now I'm going to use a length of 6 inches. Now, in reality, out to this dotted line and to this dotted line, the distance there is about 14.7 inches. So I'm a little bit under half that distance. So as I said, that's probably conservative, but let's go ahead and do the calculation. So I do that ratio calculation of H over L. So that's 1¼ inches divided by 6 inches. So you come along here, that is 0.21. So 0.21, that's right in this area. So we want to look at this curve and this curve. Now right here, I know this one's 0.9 for this condition. That's no problem. I'm going to have to do a little bit of estimate up here. So it's a little bit over 3.6. So I picked 3.7 and then for the free edge one, 0.9. So then you plug all these values in here. I get 582 pounds of compression for the fixed edge case and 141 pounds of compression for the free edge case. So as long as the compression that I calculate for the skin having to be able to handle up here is less than 147 pounds, I'm confident that the skin can handle it with no problem. If I calculate I need more than 600 pounds, I think there's a serious problem. The skin probably can't handle that compression load. If I'm somewhere in between, I'm not sure. I'm going to have to do some testing. Now, if my compression loads are less than 141 pounds, I can actually move these rivets farther apart and save some weight, hopefully. So I want to do some other dimensions here for that rivet spacing also. So I calculated for 3 inch and for 2 inch. So let's look at the results. So like I said, for the 1¼ inch rivet spacing, we got a range that we can handle from 141 to 582 pounds. That's good. For our 2 inch spacing, it's 55 pounds to 240 pounds, so it dropped quite a bit, just adding 3/4 of an inch. And then for 3 inch spacing, it drops a lot. It's about 30 pounds to 120 pounds. But on that outer rib, out near the tip, that might be close to the amount of skin compression we have out there. So we might be able to have fewer rivets in that rib out toward the tip. So now what I need to do is actually calculate those skin loads that we're going to have on the wings. Well guys, thanks for watching. Until next time.